welcome everyone to our March edition of SCDT-FlexE Centre Webinar series on flexible electronics. So after a lot of attempts, finally, I'm really glad Professor Parashuraman Swaminathan is in a position to give this webinar. So more about that, about the webinar itself from the chair of today's session. Today, we are also very happy to have Professor Jayaraman Shankar as the chair for this session. As is the practice, I would like to introduce the chair as well, so that all our participants can know about the different people who are working on flexible electronics across the country. So, Professor Jayaraman Shankar, he did his bachelor's in chemistry at Vivekananda College, Madurai Kamaraj University, and then continued for MSc at Madura College in the same university. And then he came to IIT Kanpur for doing his PhD, which he did under the supervision of Professor T.K. Chandrasekhar. Then went on to do a postdoc as the JSPS Fellow in the Graduate School of Science, Kyoto University in Japan. His host there was Professor Atsuhiro Osuka. And then he came back to India and joined IISER Bhopal. Currently, he's a professor there. And what I understand is he has been all the deans there except Dosa. So I guess that's one thing he will soon be in a short while. But anyway, what it means is he has been very much part of the institute building there. And as far as flexible electronics is concerned, he's actually an inorganic chemist by training, but he also is involved in organic chemistry synthesis. So he is familiar with both the worlds, which is perfect for flexible electronics. We don't care organic or inorganic. We just want to make sure that the systems work. So he especially focuses on photophysical properties of chemicals. And besides that, what I know is he has done a lot of chemical synthesis for organic photovoltaic devices. And I understand that he's also trying to do some exciting things on infrared detection as far as photodetectors are concerned, and he's making molecules for them. So we are very happy that Professor Jayaraman Shankar is the chair for this session. So hand it over to him. Over to you, Professor Jayaraman Shankar.
Thank you, Professor Iyer. And I really need to thank you because you introduced me to this vast group of experts where I wanted to learn a lot of things and then try to contribute as much as we could. And thanks once again for your generosity. And it's my pleasure today to invite today's speaker, Professor Parashuraman Swaminathan. He is a full professor at the Department of Metallurgical and Materials Engineering at IIT Madras. A brief introduction about him is that he graduated from IIT Madras with a bachelor's and master's degree in metallurgical and materials engineering in the same department. And after that, he went for his PhD at the University of Illinois at Urbana-Champaign. And he then worked as a postdoctoral fellow at Johns Hopkins before joining Intel as an engineer. And he joined IIT Madras in 2013 and currently a full professor and head of the Electronic Materials and Thin Films Laboratory. His group works on printed electronics with a focus on flexible, transparent electrodes, sensors, and low-power displays. As for my understanding about his work is that they extensively work on silver nanowires, and their group has been successful in demonstrating the science as well as the technology of this particular exotic material. And today, the talk what he is going to give is that absolutely everything about the silver nanowires as per the title. And it's my pleasure to invite Professor Parashuraman to give his lecture on this topic. And we are very excited to know about absolutely everything about this silver nanowires. As per the convention, as I heard from Professor Iyer, that we will be keeping the discussions towards the end of this talk. And if at all anyone wants any quick suggestion or any question, you can raise your hands, then we will be letting you in. Thank you. And Professor Parashuraman, it's yours now.
Yeah, Professor Shankar, thank you very much. Let me first begin by sharing my screen. Okay. Are my slides visible?
Yes, yeah, very much.
Perfect. Yeah. So again, Professor Shankar, thank you very much for the introduction, and thanks also to Professor Iyer for giving me this opportunity to actually talk about our work. I've been part of this webinar series maybe right from the beginning, managed to attend most of the talks, and it's actually a very good forum, to get people together and really learn about what is happening in the area of flexible electronics, not only in India, but also people working in other countries. So as Professor Shankar said, our group mainly works on silver nanowires, which is why the title of this today's talk is going to be about what are silver nanowires good for. In case you're wondering about the title, it's actually a rip of a song by Edwin Starr. I think it was a song in the 1970s. The lyrics of the song was war. What is it good for? Absolutely nothing. So I just changed the title to say silver nanowires, what are they good for? And hopefully I will convince you that it's good for absolutely everything. Now, the reason why we got interested in silver nanowires is because we are interested in transparent electrodes, transparent conducting electrodes. So it just simply means we want films that have good electrical conductivity, but at the same time, they also have good optical transparency. So I can actually see through them. Now, if you see this particular plot, I ideally want to be in the bottom, the top left corner. I want as low a sheet resistance as possible and as high a transmittance. Just to give you a frame of reference, a glass has a transparency of around 95%. So the closer you are to glass, obviously the better it is. Now, there are a lot of materials that people use to do this. And people normally go by two approaches. They initially start with a transparent material, and then they do something to improve its conductivity. So this is typically what people do when they use something like indium tin oxide or aluminum doped zinc oxide. These are typically wide band gap semiconductors, so they're transparent. And then by doping, they improve the electrical conductivity. Unfortunately, there's an issue with this. These are all ceramics, so they are brittle. So especially if you're looking at flexible applications, they would not really work out. The other approach is you start with some sort of a conducting material, and usually these are metals because metals have very good electrical conductivity, and you do something to improve the transparency. One way to do this, of course, is to have really thin metal films. So these are called ultra thin metal films. And again, there is a big challenge as to how you actually grow ultra thin, ultra smooth films. You can have regular metal meshes, but growing these are sort of difficult because they involve additional processing steps. The most common approach, and the one that we also use in the group, is to have a random distribution of metallic nanowires. And when we say metallic nanowires, mostly we focus on silver nanowires. Now, because I have metallic nanowires, and because these are metals, they are good conductors. At the same time, because they are wires and a random arrangement, there is enough gap between the wires such that light can pass through, and then this material also becomes transparent. So nanowires belong to a broad set of nanostructures that we call one-dimensional nanostructures. So these are structures where the length is large. I'll tell you what large means in a minute. And the confinement happens in the diameter or in the radial direction. So we can define an aspect ratio for these structures, which is the ratio of the length to the diameter. Now, typically nanowires or even nanofibers are structures whose aspect ratio is large. And by large, people typically say anything above 100 could be taken to be a nanowire. This is not an exact definition. There are other books that would say 200 or 500, but typically 100 is taken to be sort of a base aspect ratio. So this would mean if I have wires that are a few tens of nanometers in diameter, then I'm looking at lengths that are a few microns and beyond a few microns. If the aspect ratio is smaller, you would call them nanorods, you have nanotubes. They are also one-dimensional structures, but they're not so long. We are interested in nanowires, and ideally we want as large an aspect ratio as possible because this gives us a really good transparency. So we are not the only group that's really interested in silver nanowires. So I did a quick Scopus search a few days back where I used the keyword silver nanowires as a phrase. And I wanted to see how many papers are published. So if you look at the last 23 odd years, you have close to 5,000 documents that are being published in this area. So documents are mostly, you could say, patents, conference proceedings, but most of them are essentially journal articles. And you can clearly see that the interest in this area is growing with a more number of papers being published in the recent time. And in 2023, where we are only now in March, we already have around 100 papers in this area. We also looked at, okay, these are the papers on silver nanowires. What are essentially the other keywords? What are the applications that they are used for? And mostly you can see that nearly 40% of this is related to some form of transparent electrodes, which is the most commonly used form of silver nanowires. But there is also some interest for sensors, for energy applications, for bio applications, a smaller portion for displays, and so on. And I will also talk about some of our work in these other areas, except for bio, because that's something we are just starting out. So how do we actually make nanowires? Again, there are a wide variety of techniques, both physical and chemical. But the most commonly used technique is the chemical synthesis technique, and it's called the polyol process. So you start with a silver nitrate, so essentially a silver salt, which is reduced in the presence of PVP, polyvinyl pyrrolidone, and iron fluoride. Typically, this is done in an oil bath, which helps to regulate the temperature. And by this process, you would get silver nanowires. So we started off with this work, and initially we were able to produce wires of around 80 nanometers in diameter, lengths of somewhere around 8 to 10 microns. So you're looking at an aspect ratio of, maybe 100. So then we wanted to try and understand the process parameters. So we're trying to see what we can do in order to increase the aspect ratio. So essentially, we want longer wires and shorter diameters depending upon the process. So we tried to look at the polyol process itself, and we realized that PVP is not only acting as a reducing agent, but it also helps stabilize the wires. So what we did is, instead of using PVP of a single molecular weight, we used a mixture, one with a lower and then a higher molecular weight, and then we varied the ratios. So from this table, you can see that as the ratio of PVP to the precursor, the silver nitrate, is increasing, we are increasing the length of the wire. So you're going from nearly 19 to 37, so jumping up by twice. While at the same time, the diameter decreases, not much, but it does decrease slightly. And correspondingly, the aspect ratio also increases. So one technique that we found is just by varying the mixture, keeping everything else constant, we can play around with the length and the diameter. These are just some scanning electron microscopy SEM images showing the various wires, and these are just slightly higher resolution images of these. Then we said, okay, so this is the regular polyol process, something that you would use in an oil bath. So then we tried variations with this, where we actually did the synthesis in a stainless steel reactor, something that people normally use for hydrothermal synthesis. And we were arguing, or we were thinking that if we increase the time, then essentially we can grow the wires longer. We also did some experiments with hydrothermal synthesis. And again, we can do this in stainless steel autoclave, again for much longer time. And again, the goal is to see if we can improve the length of the wires. And we did similar things where we changed the ratio of the PVPs. And through this process, we were actually able to grow nanowires that were a few, more than 100 micrometers in length, with the diameter was slightly higher. It was closer to 100 nanometers or slightly more than 100 nanometers, but we were actually able to get really long wires. And just to give you the data, so you can see that we are able to get length by varying the PVP combination. So somewhere around more than 120 to 140 micrometers, and we are reaching aspect ratios of around 1,000. So essentially, we now have some control over how these nanowires grow. We're still trying to understand exactly the growth mechanism. But more importantly, we are able to produce nanowires with actually different lengths and diameters depending on the particular application. So there are certain applications where you may not need such high aspect ratios because the focus may be on the electrical conductivity. There may be applications where you need really long wires, especially if you're doing stuff like spin coating or spray coating, where transparency is key. So we can now sort of control this aspect ratio over a wide range. So not only are we making nanowires in the lab, so we also purchased commercial nanowires just so that in parallel we could investigate these. So many of the results that I will be showing you in the subsequent slides are used or based out of these commercial nanowires. But the goal is maybe in a year or two, we will all have in-house nanowires that we can use for our research work. So we have the nanowires. How do we actually make a thin film? Because ultimately that's what we want to do. So if I want uniform coating, there are different techniques, Mayer rod coating, screen printing, brush painting, all of those. The simplest, of course, is spin coating, and that's a technique again that we use if I want to make uniform layers of silver nanowires. So we did that. We tried to optimize the spin coating conditions, and basically we looked at the spin speed, and we also varied the concentration of the nanowires. So 1, 2, and 3 essentially means I have more nanowires going from top to bottom. More wires means more silver, and obviously more silver means lower sheet resistance. That's what we see. The transmittance behavior is slightly reversed. If I have more wires, then obviously I will have more scattering from the light, which means more wires means lower transmittance. So on one way, this is good, but on the other hand, this is bad. So typically what people do is they combine the sheet resistance and the transmittance into a single parameter, which they call the figure of merit. We follow what is called the hack figure of merit, which is transmittance to the power 10 divided by the sheet resistance. But there are other groups that use slightly different parameters, and each has its advantage or disadvantage. But this is the standard one that we use. So if you go by using this figure of merit, we are able to obtain the highest figure of merit for somewhere in between. So we are at 2 milligrams per ml. So not too many nanowires. At the same time, we have enough wires to have low sheet resistance and good enough transmittance. Now, one of the issues with spin coating or any of the other techniques that I showed earlier is that it allows you to get uniform film. But if I want to form patterns, I actually have to do additional things. So if we wanted to actually do pattern deposition, because that's our interest, so we do pattern deposition by a technique that's called a direct writing technique. And this is actually a custom built direct writer system. that students from C5, which is the Center for Innovation in IIT Madras, they built for us. So in this system, I have a substrate that can move in one direction. I'm calling it the X direction. I have my dispersion, which is silver nanowires or composites, which I will talk in the subsequent slides. These are dispersed in some solvent, and it is taken in a syringe and it is extruded through a needle. This assembly can move in the perpendicular direction to the substrate. So let's call this the Y direction. And I can dispense the ink wherever I want to, depending upon whatever pattern I have. So this pattern is digital, so it's fed in through the computer. And from the command, I can print whatever pattern I want to print. This is a more recent direct writer that we purchased. I do have some videos of this, but I'm not sure how it would turn out when I'm transmitting. But you can always go and look at our YouTube channel, and we have a variety of videos of actually making printed patterns. So what are the advantages of using direct writing? So one of the advantages of our system is that we can actually accommodate a wide range of viscosities. So typical inkjet printers can only take inks which have low viscosity, so they are similar to, say, water, so they're highly flowable. Techniques like screen printing take what are called high viscous inks or even paste. Through direct writing, I can not only print these highly fluid inks, but I can also print paste which are similar to screen printing paste. So essentially, we can access this entire viscosity range. We can also use nozzles of different diameters. So especially for the longer wires, I can also print them or deposit them by just using larger nozzles. Of course, the drawback is larger wires will have poorer resolution. But for the kind of applications that we are interested in, this has really not been an issue so far. So I've told you that we can have silver nanowires. We can make dispersion, which we can actually then print. So let me go ahead and show you some of our results. So we start with pure silver nanowires, and this is printed on a PET substrate. So when I say one pass, I essentially mean I have one layer of silver nanowires. On top of it, I add another layer that's 2 pass, and one more layer that's 3 pass. And you can see from the results, the more nanowires I have, obviously lower is the sheet resistance. But at the same time, more nanowires I have, lower is the transmittance. A one-pass pattern has a transmittance that's more than 90%. So you can actually see, you can't really see the design because it's pretty transparent. You just see through it. But a 3-pass pattern has a transmittance of only 75%. So you can actually see a hazy background, or you can see the background through this hazy layer. So what did we do with these silver nanowires? So initially we thought, let's try to make some sort of a touch sensor. And we are mostly interested in a capacitive sensor. The idea behind a capacitive sensor is pretty straightforward. You have 2 conductors. There is a dielectric. When you touch, your finger basically changes the electric field, and that creates a capacitance change, and that can be measured. Now, because I can actually print these structures, we went for what is called an in-plane design. So this is one electrode. This is the second electrode. So you can see that they are separated. We cover them up with a dielectric, and that becomes our sensor structure. So this is an example of our fabrication process. We start off with a PET sheet. PET is polyethylene terephthalate, so it's essentially transparent, highly flexible. Then we print the electrodes. We can dry them at pretty low temperature, so 100 degrees C, all the solvent evaporates. Then we drop cast dielectric. So we use PDMS, polydimethyl siloxane, which is also a transparent encapsulant. And again, this is dried at pretty low temperature. Once we have this, this is our structure. And this is just the picture or an image of our sensor. So we actually have a 2x2 sensor. There are 1, 2, 3, and 4 sensors on this block. Can barely make out the lines corresponding to the electrode. So as I said, whenever we touch, we change the capacitance, and this capacitance change can be measured. So one of the issues with pure silver nanowires is that its surface adhesion is not very good. So in the previous slide, if I had not encapsulated my nanowires, the moment I touch them, they would actually come off with my fingers. So they're not very good adherent. So to improve the adhesion, we mixed silver nanowires with another conducting polymer that's called P.PSS. This is widely used in the organic electronics industry. Through this, we were able to make a nanocomposite, which is also printable. And as you can see, the nanocomposite also has a low sheet resistance and also has very good transmittance. So again, this composite will also work as a transparent conducting electrode. At the same time, it has much better thermal stability, and it also has very good surface adhesion. I'm not showing those results here, but we did do tests to make sure that this is actually much better than pure silver nanowires. So now we have this. So we decided we'll do something different. So we fabricated a dual band Wi-Fi antenna. So this is an antenna that works in the Wi-Fi frequency range, but it actually has 2 bands. One, I think, at 2.2, the other at 5.6 gigahertz. Now, this is a flexible, transparent antenna, and we also tested this against a commercial antenna that we purchased offline, and we find that the performance of this antenna is comparable to a commercial one. Then we said, what else can we do with this? And we were really interested to make these flexible heaters. So this is our heater structure. So you have PET, which is the substrate. Then I have a layer of my composite, and then I encapsulate this with PDMS, simply because if I expose silver to atmosphere for a long time, it's anyway going to oxidize. So we have this structure, and this structure works really well as a heater. So we were able to, we did a simple step experiment where we varied the voltage in steps of 0.5 volts for different times. And we recorded the current, so we know the resistance. We can also measure the temperature. We used a simple IR camera to do that. And based on this, I can get a resistance versus temperature plot. And that gives me the temperature coefficient of resistance. We were interested only in the range below 100 degrees. And we find that the TCR is more or less linear in this range. This is actually a pretty good response in terms of a heater. So the heater stabilizes within a couple of minutes. And even at an operating voltage of only 3 volts, we are actually able to reach 100 degrees pretty easily. Then we did other tests where we said, okay, how good is it if I keep cycling this? So we cycle this at 1 volt, which is again a pretty low voltage. The temperature rise is not too much, but we can clearly see that it is repeatable. We also cycled at higher voltages, and again we see that the heater has a very good temperature reproducibility, and also it has a very good stability. Now, one of the advantages of actually using a printer is that I don't have to have a heater that is uniform. I can actually go ahead and make various patterns, which means these patterns, one advantage is you can actually save material because I don't have to coat a uniform layer, but it also allows me to introduce different types of temperature gradients within a single substrate, which can be used for other kinds of applications. So in collaboration with our industrial partners, we have been looking at various pattern heaters. One of the ideas is to use silver nanoparticles as an outer layer and then fill them with nanowires inside. So this is just a simple nanoparticle heater. So now there are no nanowires. We just print nanoparticles. Nanoparticles are not transparent, but they have much lower sheet resistance compared to nanowires. Again, we tested this and then we found that this is uniform. And extrapolating from this, we essentially said we will make much more larger heaters. These have especially some applications in the automotive industry, especially because you want to use these heaters as defoggers, especially in the windows of automobiles. So there is some interest towards actually seeing if we can scale this up to get a uniform pattern, over at least tens of centimeters and see if they can then be used for these applications. So this is something that we are working on, and there are some challenges to especially printing uniform layers over large areas, which we are trying to solve. So that was an example of a heater. And then we said, can we also start to think about energy devices using these silver nanowires? So one of my students is working on making a transparent supercapacitor. So the same idea, start off with a PET, make your interdigitated electrode, but now we use gel electrolyte, which is a mixture of PVA and phosphoric acid. So that acts as the electrolyte. And again, all of these are curable at low temperature, so I can also make this flexible. This again is a picture of the fabricated supercapacitor. So it has again a good transparency. And we also did various electrochemical tests, and we are currently analyzing the data. But it seems that 0.1 silver nanowires with P.PSS seems to be best in terms of stability and also being able to sustain various scan rates. The goal, of course, is to use these sort of supercapacitors to power different electronic devices. The next thing we're interested in is, of course, can we actually use nanowires for a display? Silver nanowires can't be the active layer for any display because typically these are some sort of semiconductors. And of course, the most common structure is an organic LED structure, which is a multi-layer structure having an emissive and a conducting layer. Typically, these are organic polymers. But we are interested in sort of low power, low cost displays that can be used for signages or interactive posters, where essentially OLEDs are too expensive and are not used. So one of my students came up with this idea of actually mixing silver nanowires with essentially powders which are called thermochromic powders. So these are materials that are colored at room temperature, so you can actually get different colors. But when you heat them up, typically around 40-45 degrees C, so not very high, they will actually bleach. And when you cool them, they get back their original color. So these are called thermochromic materials. So the idea was to mix these thermochromic particles with silver nanowires to create a sort of printable dispersion. So this dispersion I can heat by passing current, because whenever I pass current through a metal, there will be heat generated, that's standard Joule heating. That heat generated can change the color of these particles. And when I switch off the current, so when I allow it to cool, I can go back to my colored state. So I essentially have an electro-thermochromic dispersion. Why electro? Because I need to supply some electric current, but the process of color change is essentially because of these thermochromic powders. And again, we did various optimizations, varying the amount of nanowires and the amount of the ink, deciding how many layers to print, and we were able to obtain uniform film. This is just SEM image. So these are the thermochromic particles. They're typically a few microns. And you can see that there is a whole lace or a network of nanowires surrounding these. The phase transition in this particular case, going from colored to bleached happens somewhere around 35 degrees. And when you cool back down, there's obviously a kinetic lag, but by room temperature, you get back the original color. We also did some color parameters. So when we apply the voltage, the inks all become bleached, and essentially you can see the red corresponds to the bleached reflectance, so something that allows light to pass through. But without voltage at room temperature, they're going to have different colors. So you can have black, you have some form of red, there's orange, there's blue, and so on. So in order to sort of show that these can actually be used as displays, we started off with a very simple 7-segment display. So we printed the 7-segment display by using this thermochromic ink. And we also made electrical contacts using silver nanoparticles. Now, if I want to display a particular color or a particular digit, I have to turn off the complementary digits, and I turn this off by essentially supplying current through that segment. Just to give you an example, so a 7-segment display has 1, 2, 3, 4, 5, 6, 7. So these are 7 segments. If I want to display 8, I only have to bleach this segment. Everything else is colored, so I only need to pass current through this. So that's what this IR image shows. Only the center one is being heated. If I want to display 4, I want to heat this, this, and this. Everything else will remain at room temperature, and this is colored. And again, you can see that here. So there are 2 advantages to this approach. The natural state of these materials is colored, which means I only need to supply current or energy to change the color. So this gives me an advantage in terms of power consumption. And it also gives me an advantage that because it's colored, I can actually have displays of different colors and get a multicolored display. Now, because I have silver nanowires in this ink, it's also conductive, which means I can cap it with PDMS and actually make it a touch sensor. So I have both a display and a touch, which are incorporated in the same layer. And then we try to look at various examples. So a simple battery indicator, we could have some sort of touch poster, so an interactive poster, and essentially some ways of multicolor complex design that we can print and implement. Of course, these are all just lab prototypes. The question is, can you actually do something useful with this? So IIT Madras has something called an MS entrepreneurship program, where the idea is we actually take these sort of technologies that are developed in the lab and then try and take it towards some useful application that can come out. So one of my students is part of this program, and his idea is to actually use these sort of units as a display unit for glucose patch. So currently the way these patches work is that they need an external reader so that whatever data is collected is transmitted through this external reader through an NFC. So unless you have an external reader, you can't really get the data off of it. So his idea is to integrate this electrothermochromic display so that we no longer need this reader and the data is directly displayed on the patch. So we have actually pre-incubated this within IIT in Nirman, and he's now working on the prototypes. And the idea is to have some sort of a strap where the bottom layer is your glucose patch. The glucose patch will communicate through an IC to our display, and then that data will essentially be transmitted or will actually be displayed. We can also have the data transmitted through a smartphone as an additional output if needed. So this is work that's ongoing, and hopefully we will have some prototypes to demonstrate either later this year or sometime early next year. So in all of the examples that I showed earlier, we had silver nanowires and we added composites to it. We added this stuff, different things to it to make composites. But these were just physical mixtures, right? There was nothing really happening in terms of electronic properties. We were still using the nanowires as just for a display kind of, or a transparent layer kind of an application. So then we were curious to see what happens if I actually mix silver nanowires with metal oxide. So the idea was we have something like zinc oxide, which is a wide bandgap semiconductor. Mix it with silver nanowires, so I get a composite. This is again printable. Now zinc oxide can absorb in the UV range because that's where its bandgap lies. And when it absorbs light, it actually creates electron hole pairs. So the idea was, can we then use the nanowires to separate these electron hole pairs and essentially use this as some form of a photodetector? So this is the final photodetector that we printed. So again, this is transparent. And because I have silver nanowires, which have very good electrical conductivity, I can actually operate this photodetector at a very low bias voltage, 0.1 volts. Typically, if you use pure zinc oxide, you're looking at voltages of around 3 or 4 volts. But because I have a nanowire backbone, I can do this at really low bias voltage. Another interesting physics to this particular system is that unlike normal photodetectors, where when you shine light, you have more current, in this particular case, when you shine light, you actually have less current. So this is called a negative photoconductance. We believe that this is because the nanowires and zinc oxide form some sort of a Schottky barrier, and that barrier, how it behaves in the presence of light, causes this negative photoconductance. So this is not the only example where this is happening. We also did some work with tungsten oxide nanowires and silver nanowires. And once again, we are observing this negative photoconductance. Interestingly, materials like zinc oxide, tungsten oxide, nickel oxide are also used for gas sensing. The question is, can we actually use these sort of composites for gas or even volatile organic sensing? Because that can essentially take us into the biosensing area. So again, we are doing some experiments to see if we can actually combine silver nanowires with some functional materials, so we can get some really interesting applications out. So if you were to look at sort of where flexible electronics comes in, especially when we talk about Industrial Revolution 4.0 or Internet of Things, is that there is going to be a lot of emphasis on building sensors. So when you think about sensors, they can be used, for health monitoring, for environmental, industrial monitoring, structural monitoring, and so on. So you're going to need some active materials to sense. You're going to need conductive lines in order to transmit the data. You're going to need maybe some displays to actually output the data. And you're going to need some way of actually powering these devices. So we have been working on different aspects on all of these problems using silver nanowires as the base. And really our goal is to see, can we sort of put all of this together and actually make these sorts of commercial sensors that we can potentially commercialize. So hopefully through this talk, I'm able to convince you that silver nanowires have a wide variety of properties, and these properties lend itself to actually applications in a variety of areas. One of the things I didn't really talk about is that nanowires also have antibacterial properties. So they can even be some interesting bio applications, but that's an area that we haven't really tapped into. Now, before I finish, I said this entire talk is about silver, but if I can have a material that's actually cheaper than silver, that's even great. So normally when people talk about noble metals, there are three: copper, silver, and gold. Gold is obviously very expensive. So if we can actually make copper nanowires, and get them to be transparent, that will also be great. So we have also started some work with our collaborator, Professor Ravi from Amritsar University, where we are getting his help in making copper nanowires. And then we're also doing some tests. We did some preliminary heater applications, but these are all spin coated. So now we have to actually go and see if we can print these. With this, I would of course like to conclude my talk by first thanking all my students. We have a group, with people from wide variety of backgrounds, and given the kind of work that we do, it's really great to have all of these people come together. I would also like to thank my collaborators, both within IIT and outside, who essentially come up with very interesting problems that we can work with them, and also our various funding agencies. Thank you very much, and I'll be happy to answer any questions. Thank you.
Thank you, Professor Parasuram. It's very interesting and really exciting set of results. And really, I enjoyed. And I'll come to my questions a little later. Let's first leave the audience to question. First is Dr. Umesh, please.
Sir, I have. Thank you for nice talk. And I have few questions. My first question is, sir, how you are choosing solvent for dispersing the wire?
So we did do a whole bunch of experiments in order to look at the various solvents. Typically, we use, for most of this work, we use ethylene glycol. We have also tried mixtures of ethylene glycol and water. But yeah, we had to do a bunch of trials. Sorry, go ahead.
Yeah. Okay. Thank you. And my next question is actually EG is not compatible with PET substrate. So how you are managing this with some surfactant or something else?
So when you say not compatible, in the sense are talking about wettability or?
Yeah, wettability, and if you put nanowire solution, generally it shrink out and it doesn't form uniform film.
So usually with PET, we tend to do UV ozone treatment prior to printing. That treatment helps us with wettability, and that in turn helps us to get smooth film. So we do some pre-treatment, yeah.
Okay, sir, are you using some type of surfactant or something, some additive or binder, something like this?
No, so the commercial nanowires, I do not know if they have a surfactant because they do not disclose, if they're using any of those things. But the wires that we grow in our lab and which we print, we don't have any surfactant, and you've not had any issues with printing those or coating those.
Okay, sir. And one more thing, you showed wide range of viscosity of the ink. It varies, varying from 1 to actually big range. So you are just changing the ratio of EG and
no, these are not silver nanowire inks. I'm just saying whatever ink you have, depending on whatever range, we can actually deposit through the direct writer system. So these are not all silver nanowires. This is just to show the diversity or the versatility of the direct writer system.
Dr. Umesh, if you can switch on your video, it will be nice.
Thank you.
Yeah, but just to be clear, there are also screen printable nanowire inks. We have tested those, so we can print those, but we were not able to observe any conductivity. So I'm not sure what the issue was. But when I say this, these are not all silver nanowires.
Yeah. So
thank you, sir.
Jennifer, and can you please switch on your video so that we can see the person who's asking question? Yeah, please.
Hello, sir. Can I?
Please go ahead.
Yeah.
Sir, thank you for an informative webinar, sir. So I'm just working on silver nanowire based transparent electrodes, sir. My area of research is to embed silver nanowire thin films between metal oxide films to enhance their transparency and conductivity. So the problem I'm facing is that adhesion was the primary problem here, sir. So you have mentioned that P.PSS to enhance adhesion. So in my case, what would you suggest to increase the adhesion with the base metal oxide film, sir? So mine is base is a metal oxide film upon which I'm coating silver nanowires.
Okay, so how are you growing the base? Is that also spin coated, or are you buying substrate?
Sir, first base I'm depositing by sputtering, sir. Top and base or sputtered metal oxide, zinc oxide metal oxide films, and in which silver nanowire commercial ink is embedded as spin coated thin films, sir. Okay. So as I said, with pure silver nanowires, we do find the adhesion to be an issue. So that's why we go for the composites. So that's probably my suggestion, to see either if we have some composites, or to see whether there are any surfactant layers that you can actually deposit on the zinc oxide before you coat the silver nanowire. Again, it's going to depend a bit on what sort of application you are looking at, because you said you have zinc oxide on both sides. So are you looking at electrical properties? Or are you just looking at light falling through? That will play a role on whether you need a adhesion layer or not. I have planned to use it as a conductor for various applications, sir.
Okay.
Simultaneously,
so then you may not want a surfactant, yeah.
Yeah, yes, sir. So in another question, sir, if you are mixing with titanium oxide nanoparticles, what and all should be noted, sir? You mentioned with zinc oxide nanoparticles. I have tried with incorporating it with titanium oxide nanoparticles. In that case, in my final result, I couldn't find any silver nanowires. All I find is TiO2 is only forming. So
that's interesting. So we have, to be honest, we have not done TiO2. So specific questions, I can't. That part I don't know. We have done both zinc oxide and tungsten oxide. The question is what ratio, how much of each you add, and usually we use the same solvent. So ideally we want both of them to be dispersed in the same solvent, and then we can mix. So where are you from? Which university are you from?
Sir, I'm from PSG Institute of Advanced Studies, Coimbatore, sir.
Okay. So one suggestion is, of course, this is a forum, so a lot of people are there, but you can always write to me separately, and I can always put you in touch with my students, and then maybe we can look at your situation more specifically, and try to give some solutions. Yeah.
Okay. Thank you. I'll write to you, sir. Thank you, sir.
Yeah. Thank you.
Dr. Chandrakant.
So it's
okay, sir.
Yeah. Sir, is the video is visible, sir?
Yeah. Please go ahead.
Oh, okay, sir. So myself also working in an inkjet printed OLED, sir. So I was wondering, sir. So first one question, like, what is the work function of your silver nanoparticle, these films?
Oh, so that's actually something we have never measured. So I know bulk silver has work function of
5 to 4.6, it depending upon for bulk.
Yeah, but I know, but because this is a composite,
yes, sir.
I'm guessing there's going to be a change. But to be honest, we never measured it because we never needed it for any of the applications.
Actually,
that's something we have to measure. Yeah.
Yeah, sir. I was hoping that we could use it for the transparent electrode, as we also made a OLED out of it with the silver. The purchased one, the silver nanoparticle. So maybe we could use yours or no. So we could.
Yeah, that's something we can explore. Only thing is these are the roughness will be an issue, right? So for OLED, I don't know what is the base substrate roughness you desire. I have a feeling that
top electrodes, sir. We could use it as a top electrodes.
That's something we can explore. But yeah, we have not done any measurement on the work function. Sorry.
Oh, okay, sir. Okay. Thank you, sir.
Okay.
Sure.
Dr. Pranab Dev.
Yeah. Thank you, sir. It was a nice talk and informative talk.
Okay.
So I was having the same question on the roughness. So basically, if I would like to use silver nanowire in case of my bottom electrode, So for making photovoltaic devices. So in that case, how do you think the roughness should be can be controlled?
So for example, if I just had pure nanowires, they will not work, because pure nanowires, you are going to have some sort of a gap, right? That's the whole idea behind using silver nanowires. With P.PSS, the composite, we are able to reduce the roughness, but still the roughness is of the order of at least a few tens of nanometers, if not more. Okay. So to be honest, I don't have an answer as to how I would use silver nanowires as a bottom electrode. Potentially you can't, is what I'm thinking. It may only serve as a top electrode, because I don't know any other way of controlling the roughness, because these are just randomly dispersed. You're just going to have some situations where 2 nanowires are on top or 3 are on top.
Yes.
So you would invariantly end up with a rough surface, is my feeling.
Okay, thank you, sir. Thank you.
At least not the kind of roughness you would expect in, say, vapor deposition.
Yeah. Okay.
Yeah.
Okay. Thank you, sir.
Professor Iyer.
Thank you, Professor Parashuraman Swaminathan. I think it was a wonderful talk, and really impressed by the range of things that nanowires can do and how you guys have gone about it. So that was really nice. In fact, a lot of questions on various things, but maybe I'll just keep it brief just to get something that immediately. You did talk about the response that is there with light, right? So how fast is this response to light? That is, can it be used for some optical applications, communication applications?
I don't think it's that fast. So,
but what range, what speed is it likely to be? It's of the order of milliseconds?
No. We are. So if you look at the time, you're actually still looking at a few hundred milliseconds is what. But we never really thought. Use it for a communication kind of application.
Okay, so you have
because these are still huge structures, right? They're still at least from the
milliseconds, I say.
Or I mean hundreds of milliseconds, or close to a second. Yeah.
Okay. Okay, but similarly, the temperature effect as well. Could you heat it with some photons? Will that help? Rather than
for the thermochromic, yes, there are ways to also heat it with light. So potentially you can do that, because the transition temperature is not very high. It's just above room temperature. So that is possible. We haven't tried that, but yeah, that might be something interesting to look at. Can you also use it as a visual indicator of a photo detector kind of thing? That's possible. Yeah.
But really neat work. Thank you.
Yeah, thank you. Yeah.
Okay. May I now? I hope there is no other questions from the audience.
I have, sir. Actually, I raised a hand. Can I ask just?
May I know?
Sure.
Yeah, please come. Yeah.
Thanks. Thank you. So a nice presentation for some, sir. I do have 3 questions. One is first question is regarding the silver nanowire synthesis. So you are using PVP structure directing agent, which is a polymer which covers the nanowire particles and guides the formation of the length of the wire. So are you removing it after the preparation, so that you can remove that polymer coated layer on the silver nanowires? And what is the yield of that product, sir? These 2 I want to know from.
So the yield, I don't have the numbers. I know polyol is not great, but hydrothermal has, I think, a better yield than polyol. But again, I don't have the numbers off the top of my head. The second question about PVP, it is still there in the dispersion. But normally when we print it or we deposit it, we typically anneal it at around 100 degrees C. That gets rid of the PVP. But yeah, we don't do anything else specific.
That means after printing, do you dip that films in some liquid to remove the such byproducts?
No, right now we are just doing annealing.
So just
I know there are also,
just
evaporates. I know there are also some chemical treatments that are done to remove PVP. We just heat it and we are fine.
Sir, my next question is about the thermochromic particles and the silver nanowires. Since you are using the temperature to change the colors, is there any phase formation between those two, silver and these particles?
So it is still just a physical mixture. There is no phase formation, but there is a phase change in the thermochromic ink. So if you see, without voltage, it's basically at room temperature. So this is your thermochromic ink XRD pattern. And when you heat it, these lines disappear, and what you see is this sort of amorphous
okay, the
signal.
particle crystalline particles are becoming some amorphous.
So I know there are reports that even say that there is some sort of incipient melting in these particles, and that's how the phase change happens. But we see those change. These are essentially silver lines, at 40 degrees. There's no change in silver because those temperatures are too low that silver is not getting affected. And there is no chemical reaction between silver and these particles.
Could you please tell me how does the color comes from the particles or with the temperature? I don't know the mechanism.
So again, these are actually a mixture of different materials. I don't remember off the top of the head. What I can do is, here's the reference. I think in the supporting information, we have actually talked about how color is obtained. Maybe that would be a good place for you to go.
I'll look into it. I know. So
Sure.
one more last question. So
Sure.
usually while you're doing this design of the equipments in product based level. So what my question is, how do you find better design before choosing the random experiments, like maximum amount of cross section area required for such a design, or a thickness of the films or coating required? So without doing the multiple experiments, what is the criteria that we can follow while designing such
so I know there's a whole branch which is called design of experiments, which basically looks at how do I optimize the various parameters. For most of what we are doing, it's still lab based. So we still say, okay, we will vary one parameter, study its effect, and vary the others. But I think especially when we come to scale up, we will have to do that. We'll have to probably do a DOE kind of approach, where we see, okay, this is the parameter I'm interested in. What parameter causes the maximum change? And then based on that, we would investigate. So we have not done that in detail.
Is there any modeling kind of software, sir? Like I want to know, like so that we can learn.
Modeling, okay, again, I'm not aware of. I do know there are statistic-based softwares that allow you to, I know there are various statistics terms that are used to describe this. Specifically, modeling software, I'm not aware of. It's primarily an experimental group. We mostly just do the experiments in the lab. Yeah.
That's it, sir. Thank you very much for answering. And
I
could see very product-based research from your lab. Thanks for the presentations. Once again.
Thanks. Yeah.
Okay. I think I have some time, 2-3 minutes. I will
Sure.
take from. Yeah.
Sure.
So, I need to, first of all, thank you that earlier I was not sure about the differences between nanowires, fibers, and nanotubes. I thought all of them are going to be the same, but the first slide gave me that information. When you are talking about transparency, you showed a pie chart in which you showed that the transparency is the one which is more important, right?
I guess you're talking about this, right?
Yeah. So, do you have some threshold transparency you're talking about, or you
no,
just?
I'm not saying important. I'm just saying, so we found around 5,000 papers. So then we asked, along with silver nanowires, what are the other keywords that people report? So that is a measure of what is the application. So 40% of the time, people report the keyword transparent. So which means in 40% of the papers, they're only looking at silver nanowires for transparent applications. Around 19% use it for sensors, or they have the word sensor as an additional keyword to silver nanowires. So that's what this pie chart tells you, where people are using these wires.
So ideally speaking, that all the materials, all the publications which are going to use this material, everything is going to be transparent, actually. Is it right?
That is true, but the other question you have, what is the threshold transparency? It's going to depend on the application. So just to give you an example, so some of the commercial work that we do, depending on where your silver nanowire patch is on the automobile window, they have different zones. So some zones you need transparencies greater than 85%, because they are, right where the driver's visual, the eye is. There are some applications, for example, you have, say, a windshield on the side where you can get away with 75% transparency. So even from a commercial perspective, there are different values depending on the application.
Got it. Yeah. The second one is, what was the role of ferric chloride? Because I am a chemist, so I just wanted to understand, is there really a role played by ferric chloride, or it is kind of an additive just?
So, so more than ferric chloride, so there's two things. One is you have the Cl- ion. So they help to stabilize the initial nuclei. The Fe3+ also helps in scavenging oxygen. So that also helps in preventing the nanowires from getting oxidized. But to add to your question, what happens if you don't have FeCl3 or you replace it with something else? So my postdoc, Dr. Neetu, is actually looking at different alkali based or different halide based compounds. So she's looking at sodium bromide, iodides, and so on, to see specifically what this particular additive does. So that's something we are also investigating. Yeah.
I was curious only because of the fact that when, as chemists, we used to use silver nitrate test for usually for halogen testing. So when we are adding silver nitrate with the ferric chloride, what I thought is there should not be any formation of AgCl. That's why I asked you. I hope that's not the case.
Yeah, that's not the case. It's not. Right. We are not forming AgCl. Yeah.
Right. Thank you. And the heating application which you showed, in which you are talking about the silver nanowires, is there any change in the performance with respect to the thickness of the wire?
So an individual wire is around 80 to 90 nanometers. So when you say thickness, you mean thickness of the layer, right?
Thickness of the wire, what we are using.
So typically the wires that we grow, we are having the diameter somewhere going from 80 to 100. We don't have much control over changing the thickness. So we can change the length, at least in the polyol process, we can do that. But thicknesses going from very thin wires to very thick wires, that's something we don't do. And we actually don't want them, because really thick wires also affect our transparency. So that's a study that we have not done. We ideally want to have wires which have a diameter close to 100 nanometers, slightly less, and lengths that we can vary from 10s to maybe 100 microns.
Okay, so even if it's going to be a nanowire, it is going to act as a bulk conductor, isn't it? This
exactly. So if you're asking about quantum effects, in metals, quantum effects only come when the thickness, when the dimension is of the order of a few nanometers. So I have seen papers where, at least I know there's one group in ISC where they have shown really thin silver nanowires, which are a few nanometers thick. And there they can see some sort of quantum effects, but these all behave like bulk. There are no quantum confinement effects. Yeah.
Okay. Yeah. My last question. Sorry to delay this.
No problem. Yeah.
Photo detector, whatever you are talking about, you use zinc oxide, but is there any application which you tried with some organic materials or organic polymers or something like that?
Actually, no. So that's not an area that we have expertise in. So we never really tried that, but that'll be something really interesting to try. So I need to talk to more chemists to find out, what are the possibilities there.
Yeah,
I'm from a metallurgy background, so we sort of stick to metals and maybe some semiconductors, but I know there's a whole organic world that's out there, which we can tap.
Yeah. So if you're interested, I will talk to you sometime about
this.
Yeah,
sure. That'll be great. Yeah. Thank you.
Thank you. And is there any questions from audience?
I'll just stop sharing then.
Yeah. I think if there are no more questions, please join me in thanking Professor Parasuraman for a fantastic lecture with a lot of applications. And thanks a lot, Professor Parasuraman. Yeah, I hope all
thank you very much. Yeah,
enjoyed this. Right. Yeah, thank you.
Thanks.
So thank you very much. I think this was an excellent webinar, I would say. And thank you very much, Professor Shankar, for conducting it so nicely and being patient and allowing people to ask questions. So that was very nice. And of course, the speaker, Professor Parashuraman Swaminathan, excellent presentation. And I think this is a very good work. And also, I'm wondering whether we can have some collaboration. I think Amol Kulkarni is also having a company which is making nanowires. So
and I think he had a webinar earlier. Yes.
Yeah, he had a webinar earlier. So maybe
that's something
these are already talking. So this is excellent, a great work. And thank you very much. And also the testimony for that is testament for that is so many questions are being asked. And so many people want, so that you really kindled the curiosity of a lot of people. So hopefully a lot of good things will come out of this. And also a lot of people are still online. So we are past the time. So I really appreciate the speaker, the chair, the audience. So thank you very much.